Welcome, everyone. Incredibly happy to see you again here. Probably you joined because you would like to learn more about VAE or more, maybe how many epochs to use, what batch size to use, or maybe how to obtain a vector representation. Many more besides what I mentioned, we'll be discussing on today's session. And before we will get to how to obtain the vector representation, we will explore what are the options, how we can do that with the images, with the 1D, 2D, with the RGB images, 3D or 5D with the videos, or maybe with the text. And then which approaches, tools, techniques can be used and how all of that can be comparable, what are the practical examples, and how all of that can be stored in the vector database and why. I would like to start from this point and sharing my screen, and I would like to show you this. This is, yes, this is the Wikipedia, but what is cool here is that image on the right side, variational and autoencoder neural network architecture. And because we will be building today our own variational autoencoder, so I wanted to show you the overview. Uh, for the first view, quite simple. We have an encoder and several dense layers, and yeah, which helping us to decrease and or actually not decrease, but to flatten. It's called a flatten when we are taking an image, for example, a 2D image, making it flatten 1D, and we had an image in case of the MNIST, which is 28 by 28, and we are doing it flattened, and we are getting 700 pixels. And then transforming it to the latent space. This is the vector representation of an object. And then we need a decoder to do the actually same through dense layers and get an output. Thing is, if we will run it for one time, most probably the object which we are now encoding and decoding will not look the same. So we will need to create our own variational autoencoder model and training and run these for several times so the model can learn and we can get the quite similar output. And you can ask why we need to do the flattening, because there is a lot of convolutional layers models which can be reused and they can handle the 2D images. Yes, they do. Another thing with the 2D images or the fully connected networks, the flattening still required. And also it's a great way to understand how to obtain the vector representation of an object. Quite a simple, fast way. So let's try it. Let's make it happen. Good. Double checking that I'm sharing the right element. No, okay. So I want to share the vector DB, this one. Good. So on top, you can see the image what we just went through. Then let's import the dependencies and the packages and models. What we will need firstly is NumPy because we'll be using the errors, and I'm using a Python as you can see. NumPy is a good open source product for working with the errors. Now MATLAB PyPlot. This is MATLAB-like plots. Why I need this? I would like to show you visually how this vector representation looks like. I think it's easier to understand and work with that later. Of course, TensorFlow, kudos to Google, great tool for anything related to machine learning. I do using it. Also, beside the advantages, uh, take into account that Google team, whenever the version of Python is changing, taking their time to also adapt the TensorFlow. For example, now we're on the latest version of Python and it's been 3 months yet and TensorFlow still not supporting it. So for example, to run this test or to write this code, I had to move back the Python version to actually use the TensorFlow and the Keras function. Keras is an API who is new to this API for TensorFlow, which we can use with all the required elements. Like dense layers, I mentioned we'll be using the fully connected neural network, so we need dense layers to flatten our object in our case, it will be MNIST images, handwritten digits. Now losing optimizers model loses. Oh, I just found I might need to do some CR of this code because several elements imported several times, which there is no need on it. So just a bit of a not really clean code. So we'll work on that. Now, loading data and training set. So data in the training set, and you can see I mentioned already to be loading NIST. The next part is reshape the images. That's exactly what we discussed here through the dense layers. Yes, and take a look. We had previously, when first it was loaded, we had 60,000 our training images. Each one was 28 by 28. Now, after the flattening, reshaping the images, we got again 60,000, but now each one is 784 pixels. Exactly. Now we got 1D images, which can easily be passed to the encoder, then to our VAE model, so we can get the vector representation. Okay, next point is some neural network parameters. And interesting part here is these numbers, 50 epoch. There is no good solution how many epochs to use. I do recommend start from lower number, and then if you can see if your loss is improving, good, good. You can stop learning, but if you can see that you still the images are still getting a bit of noise and you need to run it more. So I added 50. There is no golden rule here. Try on your own. Same with the batch size. I added 100. Um, if you will add more, that might impact your results. So I do recommend going from. So actually, there is no again golden rule here. My practical showed me that that's I'm getting the best, not the best, not very good word. I'm getting quite good results by using 100 instantly by one. Now, I didn't mention one important thing. 50-50, and who is new to all of this machine learning part and writing your own autoencoders, virtual autoencoders. Uh, 50 means that our model will go 50 times using these 60,000 images. So basically, our system will go through millions of images. Just multiply 6 by 3, we got 3 millions of images um, when during all this process. So quite insane, right? So, but each time, and we have 50 times, system will be using 60,000 images to learn, to go through, to improve the results. Yep. Now, dense layers. So two, because we'll be using mixed images, if you will work with the text, with more sophisticated elements that you will need for object recognition, you might want to use more. So how to work with this? If you see that your image not clear enough like this, you want to have more precise, use more. If it's still good, decrease number of um, dense, latent layers. Okay, perfect. Now I just did a plot of the image from our data. We can do anything else. For example, this still quite fine. Here we go. So this is how our image is stored. Now, simple function. We need the function to start loading our data to our encoder. Take a look on the top. So we will need encoder. Then we will get finally the vector representation, and then we will talk about encoder. In the code, I will add both encoder and encoder, and then our virtual autoencoders, which will create the vector representation. So starting with encoder, I found this great example in the internet. Unfortunately, it has an issue with the tensor with this one, what we had just loaded with API with the keras from TensorFlow, and it was recommending me to create a layer on top of it. So I basically rewrote everything and created on this way. So feel free to try use. I already pushed it to GitHub to my account, so you can just grab a code and run it on your own. Take a look. I'll just run it here. Yeah, so it's no errors. Everything is fine. Then it goes decoder. Decoder we are running. So you see we need to get it from 2, then dense layer 128 to 156, and we'll get again to 784. And the model. This is actually the model and the training loop where we are training. Here, what can be the next step in improvement is what I mentioned, to stop when we see the result is quite good. We can do the intentional stop. Let's run and see how it will go. Take a look. Let me double check. So it will print our epochs and will print the values for each epoch. Okay, good. Let's run it and let's see. Okay, cool. So it's running, it's running. Oh, good. Uh-huh. Perfect. So we can see 784. It's good. So it's all flattened, all great. And now this is the data showing how our model is training, how our model is is learning. Let's look on the first uh, visible batch. So as you can see, all the numbers are between 69, 69 and 5, 69 and 4. So between 69 and 4 until 69 and 5. So it's good. So this indicates that each batch has a similar loss. So it's not massive one. Now looking on closely on the data here, is it is it decreasing? Oh, good. So you can see that from time it's actually decreasing 62, 59, and the model is still running. So let's try to get it 19, 18, good. So the decrease in the model, it means that its model is learning. So we have a decrease in the loss. 1 second. Right. As you can see, now I scroll to the last batch and we have here 16. So this is the sign that our model is learning. The size is big, the deviation is not that big. So the learning process went quite good. So we are now at 16 and yeah, the distance between the step is not really that high. So we have 16 and 2 and max 16 and 4. Very good. All right, let's build encoders and run, finally use our MATLAB-like plot so we can see the results of our learning. Let's do this and run the plot. Good. It's running. Hey, we got it. Wow, impressive. Can you see these? So we have sorted out elements with 1, with zeros, 9s are also together, 6, 7s are also together. I love it. Imagine this. This is the vector embeddings represented as a 2D embedding. This is how we were able to encode our 2D images, transform flatten one to 1D, and that's the representation. Let me show you the code, how it looks actually from the vector side. So let's take a few examples. Let's take 1, 0. So it's text flag 10, which is 28 by 28, 13. It's still 0. Yeah, more or less. Take a look on the variables. We have this one. And now take a look on that one. And 1. So we have 0, 0, 1. And let's look on it calculated vectors of the specific elements. Take a look. This is the calculated vector of 1, and now 1, 0, another 0, and the 1. You see? It's very common. So they're quite similar ones. That's the beauty of using vector representations, because you can play this, you can do this with a signs, even with a text. To do this with a text, let's import, and for this I will use the paraphrase model, LM model, and I'm having some error here. Let me quickly check what is that. Failed transform integration because of the user flow. Oh, that's not a problem. Let's do it. So we can do it now. Okay. Let's take a look. What's happening here? Failed to import transforms model because of the following error. Okay, trace back, fine, that's okay. TF Keras, I do have a TF Keras package. Backward compatibility. Okay, so what I need to do to run to see the same vector representation, not only the digits, but I want to play with the text and show you guys. So that I need to open the bash terminal and install a few more packages. Backward compatibility TF-Keras package and maybe something else. Checking. It is because the following. Okay, that's fine. Import transforming model. Fine. Good. Okay, so quickly installing the one and let's run and see what we can get. So let's do all this together. We'll share the terminal so you also can see where we are now. Okay. Previously, I did install this package. Take a look. Okay, where it is? Yep. Here we go. Yeah, I did install it, Sentence Transformers, and now I still in my virtual environment that is good. So let's install TF-Keras backward compatibility. Running, and most probably I will need to restart the kernel, so probably we'll have to rerun all of that. That's a downside, that's a cons of not having it, but yeah, let's try. I don't think it will work because it's not yet connected. However, there are chances. No, of course not. Okay, so let's restart then. Let's restart the kernel, and then there will be a few more errors because we will need to run it from scratch. Okay, it's good. It's good. It's good. So what we have here, let's take a look. I'm not sharing. Sorry. Stop sharing. So let's look again. Sorry for sharing the terminal. Now let's switch to my Jupyter VectorDB. Okay, we are back. Good. So internally, you saw I installed the model, and now let's add some sentences. Firstly, let's say this. Okay. Oops. Uh, any random sentence. I just want to show you what will be the vector representation using the LLM model. So we are not only specifically switching to a vector, but the system is trying to find the logic in there and combine more or less similar phrases. So let me show you the beauty of it, the beauty of the semantic search, because that's how it works. This is how it's built. Now we need to type the second sentence, which is quite in the same topic. Forest looks amazing, grass is green. The animals, um, looking for a food. Rainy. TV is not well. So TV is not functioning well. Motherboard is broken. So I specifically wrote the third sentence completely out of context. Everything's fine here, yeah. To compare their vectors embeddings. One good, one good. Okay, then let's run the embedding model and we'll print the embeddings. So we'll do it in this way. Okay, go. Love it, love it. Take a look. So the first and the second sentence, they are somehow familiar, similar. So their vector embeddings looks close to each other. But then the next one, we have -1. It's quite far, quite different. Let's do another one. Let's plot all of that and compare. No model name Seaborn. Ooh, okay. Got it. So I need to install Seaborn also to run these type of things. Hadn't been import MATLAB, but I did import it before. So I also need to import Seaborn. Sure. Second, and I will make that happen. So switching back to terminal, and let's install the Seaborn. Pum, pum, pum. Went good. So switching back to VectorDB. Great. Okay. Again, most probably I will need to restart the kernel. Maybe not. You never know, you know. Sometimes in Jupyter it's just working pretty well. Sometimes it's like, wow, you saw it, guys. Look at this. This is how we can compare the vector representations of our text phrases before. And you see, some of them looks quite familiar. Another one is different. Let's compare the first and second and then the third one. Nice, 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 nice. So there is also another few steps. What we can do here is to measure the distance between uh, these images and sentence embeddings. So there are a few ways how we can calculate the distance between two vectors. And I'm thinking I will do that in next videos for those who are really interested in playing with these elements, because it's quite also interesting topic. So take a look. So what we did today, we today learned with you how to obtain the vector data of an object. We did it with an image, 2D, flatten it, got it 1D, and we did it with a text, which also got numbers. So what are you doing after that? You're placing it in the vector DB and you can play with it what you want. I will have a specific another video on that, how we can store in database, how we can use it on practical case even more. And yeah, so next video will be on VectorDB, and next video will be about the 5D images and convolutional networks, so convolutional layers. So we will not be doing flattening, we will be directly using the 5D video, maybe 3D with the RGB with colors, and see how we can achieve the next steps. If you have any questions, write suggestions right under the video, and let me stop sharing. I hope you learned today or at least found something interesting. And if you have any questions, add this below the video. I will be answering instantly and on everything. Thank you. Thank you for being here. Thank you for watching. Have a fantastic day.